My name is Ruchi Gupta. I am from University of Birmingham in United Kingdom. I'm giving this presentation on behalf of my PhD student, Victoria Wensley. She has graduated since then, so I'm giving this presentation. I would like to start by showing you a picture of our campus. This is the center of our campus. It's a very green campus, and we are very proud of our iconic clock tower. It's the tallest freestanding clock tower in the world, and this is an icon of our building. To the right of the center of the campus is our School of Chemistry, which is where I'm based. And since last year, we have a new home, which is called Molecular Sciences Building. So the name of the building very much reflects the multidisciplinary research that happens in our school. In my research group, very broadly speaking, we have three strands of research. The first one is on optical sensors. We work on hydrogels for sample preparation. And finally, we work on acoustofluidics for high throughput chemical and biological assays. So today's presentation will be very much focused on optical sensors, particularly for measuring pH. So as we know, water is essential for life, but it's becoming more challenging to provide safe drinking water because of increasing global population and increasing pollution. One of the important parameters of water quality is pH value. And if we look at US Environmental Protection Agency, the recommended pH value for drinking water is between 6.5 and 8.5. So below this pH, water can contain a lot more metal ions, which is harmful. And above this pH, it can contain calcium, which cause these white scales when we boil our kettles, for example. And also water can taste bitter. So what are the current ways of measuring pH? Well, firstly, there are colorimetric based paper strips, but these approaches do not allow continuous monitoring of water, which is essential if we want to do real-time water quality management. So we have also used electrochemical glass electrodes. So these drift over time and requires frequent calibration, and they are also quite prone to fouling. And then the final technique is optical sensors, particularly based on refractive index measurements. And these ones, they could use pH responsive hydrogels in combination with different transducers like photonic crystals, SPR, and fiber grating. In today's presentation, I would like to introduce another type of sensor that we have developed in my group, and that's called Leaky Waveguide sensors. So Leaky Waveguides, they are a few micron thick, low refractive index film deposited on a glass substrate. So this film has a lower refractive index than substrate, and we can make them out of materials such as hydrogels. So if you look at this structure in more detail, oh, by the way, the cover is the sample solution that we would like to measure. At the waveguide cover interface, light experiences total internal reflection and is completely reflected back in the film. But at the waveguide substrate interface, light only experiences Fresnel reflection. So some of the light leaks out at the waveguide substrate interface. And hence these waveguides are called leaky. They are not true waveguides. Nevertheless, light can travel in these low index materials for up to a few millimeters, and it can interact with analyte that we would like to measure. Okay, so this confinement of light happens at specific angles of incidence called resonance angles. And the resonance angle is given by this expression. So it's inverse of capital N by NS, where capital N is the mode index of the waveguide and is given by the mode equation. I won't go into how we derive this expression, but what I want to highlight is that the mode index, capital N, is a function of the refractive index of the waveguide, which is NW, and the thickness of the waveguide. So if we make these waveguides using pH responsive materials, the refractive index and the thickness of the waveguide film can change, which in turn can change capital N and hence the resonance angle. So we measure how the resonance angle is changing as the pH changes. This is the sensing mechanism. So in this work, we use a natural polymer. It's a polysaccharide called chitosan. It's derived from the shells of crabs. It's a chitin, and then it's derivatized to have primary amines. And because it has primary amines at low pH, they can be charged, which causes electrostatic repulsion and causes films to swell. And at high pH, amines are uncharged, so the film shrinks. And that causes a change in the refractive index and the thickness of the film. If we look at the pKa of chitosan, it's around 6.5, so it's expected to be responsive between pH 5 and 8, which is the range of pH that we are interested in measuring. Okay. If we look at the mode equation in more detail, we can also see that capital N depends on the refractive index of the cover layer. So this can change because of common mode effects, so such as changes in temperature and changes in sample composition. So we must be able to eliminate the effect of these variables if we want to measure pH reliably. And we can do this if we use stacked structure. So in this case, we use a pH non-responsive agarose film deposited underneath our pH-responsive chitosan waveguide. So in this stacked structure, we expect to see two resonance angles, one corresponding to chitosan, which is pH-responsive, and the other one corresponding to agarose, which is pH non-responsive. So agarose only causes changes because of common mode effects, and chitosan from pH and common mode effects. So we take a difference between the two to get much more reliable pH measurement while eliminating the effects of temperature and sample composition. We make these devices by spin coating. This is one of the instruments that we use to do our measurements. We make this by ourselves. And if we look at the path of the light, we use a light source such as a red LED, and we'll use a camera. So it's a standard CMOS camera where we capture the reflected light coming out of the leaky waveguide sensor. If we look at the image on the camera, for a leaky waveguide with chitosan or agarose waveguide, this is how the output looks like, where this black line marks the position of the resonance angle. So we measure in real time how the angle is changing as we introduce solutions of different pH. And these are some of the results. So here I'm plotting a steady state change in resonance angle as a function of pH. And for chitosan, as expected, we got a sigmoidal response as a function of pH, where the inflection point is about 6.2, which matches with the literature reported pKa value of chitosan. We can also see that the response is about a degree over a pH range of 3 to 9, which is quite huge. We can measure angle changes of about millidegrees. So this can give us, in principle, pH resolution of a millidegree, a milli units of pH. And we can also see that agarose, as expected, is not responsive to pH, and we have a relatively good device-to-device reproducibility for chitosan leaky waveguides. Here I'm showing the change in resonance angle as a function of time as we pump in different solutions of pH. So as expected, as the pH increases, the resonance angle decreases. We can also see that the sensor is reversible. So for example, pH 3, when we put a couple of times, we get the same signal. And the response time is about 2 to 5 minutes, which is sufficient for typical pH monitoring. Okay. Then moving on to the stack structure, as I explained before, we got two resonance angles, one corresponding to chitosan and one corresponding to agarose. And if we look at the pH response, so the difference is chitosan minus agarose response, so which are the blue scatter points. So we can see that it's responsive to pH. The response decreases slightly, so it's about now 0.6 degrees versus 1 degree that I presented before. But the key point that I would like to make is that when we change the sample composition considerably by adding glycerol, we can see that the blue scatter points, the signal is much lower than the absolute signal. So it's reduced by a factor of 7. So this is how we eliminate the common mode effects while measuring pH. So in summary, I presented a chitosan leaky waveguide, which is responsive over pH range of 5 to 8, which is the range that we are interested for drinking water quality monitoring. The response is about 1 degrees over pH 3 to 9. The sensor response is reversible, and the response time is about 2 to 5 minutes. And using stacked waveguides, we can suppress the common mode effects by up to a factor of 7 while still able to measure pH. So I would like to thank the various funding bodies, especially Process Instruments, that funded this PhD project. And finally, thank you very much. And if there is time for questions, I can take a question.